Ready? Okay. All right, everyone. I came here to show you some of the work we have been doing for the past 2 years on this project. On this very brief presentation, I'm going to show you some. Of course, I cannot explain every single decision made during the development of this project, but I'm going to try to go over the most difficult aspects and some of the pitfalls I encountered while designing this project. And at the end, I'm going to do a brief live demo so you can hopefully better understand what this is all about. All right, let's start. All right, so you can see right now on the screen two pictures of the completed board prototypes fully assembled. So what this essentially is a Linux computer. We initially started this out as a traffic light camera for traffic light intersections. However, during the process, we realized that a traffic light camera is not very different from other kind of Linux devices, like for example a tablet like this. In fact, most of the camera devices manufactured by companies like Hikvision or similar, they are, in essence, they are embedded Linux devices. So it's not. It we realized it was very. We could use most of the work we had already done and repurpose into a Linux tablet. So that's essentially what we did, and we call it Bone Vision AI, which is a project that will go soon in cross supply. It's probably gonna pre-launch this week, and you can expect the full launch in 3 or 4 months approximately. So over the course of this presentation, I'm going to try to just mention the most important aspects during development, and I will I will show you a live demo at the end. So right, we decided to do this project because at the time, which was 2 years ago now, there were pretty much almost no completely open source single board computers. Now, of course, that has changed recently. There are more options now, but that was not true 2 years ago. And at the time, computer with neural processing units were also very rare. They have become more common in the past 2 years, mostly because of the AI boom we have experienced lately. So companies like Qualcomm or Intel have tried to implement these neural processing units into their chips lately. However, at the time we started this project, this was still very rare and not very common at all. So one of the most principal aspects of this project is that we did not use any kind of compute model, and you can probably already figure it out by the board image you already saw previously. The reason for this is that we really did not want to use any compute model just because we wanted to do it fully from scratch, which was a huge motivation to us. And of course, well, this decision really cost us a lot of extra time and extra effort that maybe at the time we were really completely aware of. But anyway, I'm going to go over that in the following slides, so I'll try my best to explain it to you. Any question yet? All right. So right, I'm just gonna show you a very brief timeline explanation so you can imagine what kind of time you need to build something like this. So you can pretty much see the hardware design was not the most complicated aspect of this. The most complicated aspect about this project was developing the software because by not using any compute model available, we had to make our own image from scratch, and this was really hard for us at the time. And well, it's not only that; it's also that when you develop software, you usually want to do more improvements and fix more issues, and it's pretty much everlasting if you want. So there's no end to it. So that's pretty much the reason why you can see we have spent most of the last 2 years developing the software. The actual hardware design probably took us about 3 or 4 months. Of course, this is excluding the time we had to wait between prototypes because there was a considerable lead time between prototypes. Now, I'm not gonna go through the entire schematic, but I'm just gonna mention some of the key details we found during this stage. So one of the first aspects you want to make sure you nail down the first time is that you choose a microprocessor with very widely available documentation. You don't want to find yourself with an obscure Chinese component that no one really knows how to fix or use. Now, of course, so first and foremost, you want to ensure there's a very good community support for the platform you're choosing, because once you choose it, you're tied to it, and you pretty much this can pretty much make or break the entire work. Now, of course, it was also helpful that since the RK3566 was common in other single board computers, there were some example schematics online, which of course were not fully in line with with what we wanted to do, but it provided us a very a very stable foot to begin with, so we could study it and modify it to our own needs. Now, as for the software we chose to develop the entire hardware design, we chose KiCad because, well, if we were going to make this open source, we may as well use an open source schematic and later editor. One of the key aspects you want to make sure while choosing a microprocessor is that you make sure it's not a microprocessor with very high current consumption, because this can bring out a lot of issues later on. For example, if you have, let's say, a microprocessor with, I don't know, 10 amps of current consumption, this is going to cause you a lot of trouble, because this will really complicate the design of the DC converters when you go to design this in schematics. This is also going to make the PCB layout a lot more complicated. It's also going to make the entire fabrication a lot more expensive. So if you want to make a design with a microprocessor and you don't want to complicate yourself too much, make sure you're not choosing something that consumes a lot of current. All right. Any question at this stage? All right. Now, as for the PCB layout, that's an image I exported from KiCad. It includes all the 6 layers in the design. Now, there were a very few key aspects that really help us make this a lot easier for us. For starters, one of the main complications when developing a microprocessor design is that you have to match the track length between all the DDR lines. Luckily for us, with this specific microprocessor, this already has an internal meshing routine inside the DDR controller. So you don't really need to worry too much about matching the length on these lines. Another, now some of the other key aspects during this stage was making sure we didn't use too many layers, because it really makes it a lot more expensive, and we wanted to keep it cheap, of course. So we found a great stack up that worked great for this project, and well, you can already see it on the screen. It's a 6-layer design. You have all the signals contained between the top and the bottom layer, and then you have the ground planes next to each signal layer. Sorry. Okay. And lastly, at the middle, you have the power planes, which is really useful because it's very. This is a bit complicated. You probably are better off using dedicated power planes for this. Now, another of the key benefits of this stack-up is that since each signal transitions directly from top to bottom, there are no via stops on the design. And you also do not need to backdoor the vias with your manufacturer. All these things will increase price and decrease signal quality. So by keeping all the signals between top and bottom, we really make it a lot cheaper and also a lot more stable to manufacture. Now, of course, it was very hard to achieve this, but it was very well worth the effort. Now, as for the prototyping, the manufacturing of the prototypes, we decided we wanted to use a very low volume manufacturer, so we went with PCB way, which complied with our requirements. Now, some of these requirements are, for example, that we require a very small glass laminate inside the board. That's because, as you can see in the image, if you have if the glass laminate on the PCB is too, let's say, too discontinuous, this will make up a lot of interpair skew in your differential lines, and this can cause very graph issues. So you don't want that at all. Now, another key aspect that we talk and we arranged with PCB way back from the beginning of the layout was that we really require a very small via size, which in this case is 0.2 millimeters. You usually want to make sure that your manufacturer can comply with your required specifications, because if you finish the board layout and it turns out it's too expensive to manufacture, or maybe worse even, maybe it's not possible to manufacture at all, that would make you pretty much lose your time. You will have to make it all from the beginning. So for this kind of projects, you really want to make sure your chosen manufacturer can handle all the required specifications, and you want to make this clear from the beginning. Now, I have only talked about the hardware design at this point. Well, I have only mentioned the most important key aspects, because I'm not going to go through everything right now. But on the software side of things, and this is a lot more interesting, at least for me, for example, because when we chose to not use any kind of computer model, this meant we had no software support for the board we were making. And this was going to cause a lot of trouble and a lot of extra work. So we needed to make a new custom image for this device. And we had many actions. Actually, one of our first custom image was a Ubuntu distribution. We used we took the source code and we recompiled the kernel to accommodate for our different device tree source. However, you don't really want to use a common distribution like Ubuntu on a platform like this. So you have pretty much two options. You can either use Bootroot Linux or you can use Yocto. Now, of course, the difference between 10 is that Yocto is a lot more powerful, but it's also a lot more challenging to use. So we really did not know how to do this back then, and we did not want to set up ourselves to more hardships than we needed to. So at this point, we really chose Bootroot because it was more simple and was easier to use than Yocto. And well, this decision proved to be very good, because it was really easy to learn to use. And well, you can find most of our Bootroot code on our open source repositories, and it's really very easy to learn and anyone can use it. And by using Bootroot, we wanted to use it because it's not really a Linux distribution like Ubuntu or Debian. Bootroot is more like a tool to build Linux distributions with everything you need. So you can pretty much tailor-make your own image to your exact requirements. For example, if you actually want no bloat, for example, you're going to deploy a headless system and without any kind of screen or graphical interface, you can just remove it from the image and optimize the boot time. That's just an example. But you can really do anything with Bootroot. You can build any kind of system you need, and you can optimize for any requirement. So that's why we chose to support Bootroot first and foremost. Now, wait. Give me a second. I think the resolution is off. All right. No, I'm just gonna leave it as it is. Wait, sorry. All right. All right. Sorry. Let me fix this. All right. Wait. Here. All right. So at this point, I have only talked about the development steps of this, and I'm pretty sure most of you are may be confused about what what has been built here because we frankly have not talked about it yet. So does any of you want to know? Yeah, sure. All right. So many of the use cases, and I'm going to show you very soon, but we can. This was initially developed as a traffic light camera intersection, so that's actually one of the first use cases we deployed. That's right there over there. You can see that's our the board inside the security camera enclosure, and we use a power on internet splitter to make this work because our board didn't have power on internet capabilities from the beginning. So by using the splitter, we could take the Ethernet cable and separate the data from the power and get a USB-C power output, and we could configure this arrangement. So we had deployed this camera in the field for about an entire month. It worked perfectly without any kind of issues. Um, some of the other use cases are that you don't really require to use this as just a camera. You can also use it as a coprocessor or transcoder for any other existing camera out there. So you're not really limited to the built-in sensor on the board. You can use it with any kind of Ethernet camera out there. Now, lastly, the tablet mode, which is what you're seeing right here. This is pretty much um, the tablet mode allows for other uses, like for example, face recognition or license plate scanning with results on display. Now you can do a lot more with it. We also had you can also use it as a Linux desktop device, but well, it comes down to whatever you need it for. So as for the main program running on this, um, all right, the main program on this device is the object detection program, and you can see the specs right there. So we really wanted to optimize for performance and not try to use the CPU as less as possible. So we use SDO, which is a low-level graphics library because we did not want to use OpenCV libraries. They were very slow and they are very intensive for the CPU. So we have loaded the graphics rendering and the bounding box drawing from the CPU into the GPU with SDO. And you're going to see it very briefly. As for the AI inference task, we're using the neural processing unit for this. So again, we are trying to offload as much as possible from the CPU, which is usually not very strong on this kind of low power devices. Lastly, we multi-threaded the entire program because there were multiple system calls for the GPU and the NPU and the 2D graphics engine. So all these system calls will start the main program and increase latency on the loop, and this will have a very detrimental effect on frame rate. So multi-threading the entire program was very important. And now, well, I'm going to skip straight to the live demo because I really want you to see this. I think you may not be understanding myself, you may not be understanding me very well right now, but I'm just going to show you what this can do. All right. So this is running on the device right now. I'm going to disconnect this. So this is all being processed on the device right now, and it's running completely local without any kind of cloud computer or internet connection. So you can see the performance right there, and well, it's well. I don't want to say this myself, but I think it's very impressive. So yeah, um, so this is the main program I tried to explain to you a few moments ago, and I think it may be a lot clearer to you, a lot more clear to you right now what I've been trying to explain. So this is the performance we have achieved with this device, and it's going to be completely open source. Right now, you can already see most of our operating system code it on GitHub. I'm going to share the link very soon. As for the schematic and the hardware files, they are going to be uploaded very soon. It's just we're still cleaning it up because it's kind of a mess right now. So we really want to make sure it's organized and that people can understand it very well. All right, I'm going to connect my laptop again. Yeah, that's correct. And actually, I really want to make sure to give credit where credit is due. The SDO backend code was not made by me. It was made by Alexander. A very He's a good friend from the Raxa forum based on this computer. So the SDO backend code was made by him. So you can see his GitHub right there. And some of the other code, for example, do you have a question? All right, that's a very good question. I didn't. Building the boy root, I think it took us about. Well, it was. The thing is that once we probably had a working boy root image like in 2 or 3 weeks, but as we were going along, we realized we were missing some very important features. For example, the camera engine calibration, which makes the 3A algorithm, or for example, the GPU acceleration. So these were things we realized as we went. Now, most of the time was spent making sure everything on board worked. So all the drivers, all the peripherals, that's where most of the time was spent. And on the application side, I would calculate approximately 20% or 30% of the time was spent on the application side. Sorry, you were asking me?
No, I was asking like the SDL, like what it is used only for rendering.
Yeah, for rendering and for drawing the bounding boxes.
Okay, so is that what is that a standard open source library or is it part of Mesa that does 3D rendering and stuff?
Well, SEO is open source, but Mesa, if I remember correctly, is an open source driver. Yeah, we're not using Mesa right now. We are using the proprietary drivers. But yeah, you could use message if you want. That's fine. Yeah. Well, it was actually very surprisingly simple because, well, I can show you my. I have the entire. Sorry, I fell off stuff open. All right, 1 second. I have the entire repo right here, and can show you. So this is pretty much the MPU package which handles the AI inference task. And all right, I'm going to show you the makefile, which I believe may be more useful. And by the way, you can see this all on GitHub, so you can check it on there too. All right, so this is the makefile, and to be honest, this was like the first makefile we made for Build, and now remembering, we actually did not make this ourselves. We looked for help because we were still learning. However, you can find examples of this online. And what this does practically is it takes these libraries from here. Here, no, these two libraries, and it copies them over to the root FS system. As to be specific, it copies them over to the libraries folder. So that's pretty much it. It doesn't require much else to work. Well, this is very simple to work actually. This driver is very simple to make it work, and it was probably the easiest out of them all. If you want to know which was the most complicated driver, it was the camera engine driver, which handled the color correction and the exposure balance algorithms. That was probably the most complicated of them all. All right. Yeah. Sorry. Supports TensorFlow and any kind of AI model out there. I don't remember all the names right now, but on the documentation, it may have it right here. All right. To try. All right. I'm not going to search it over right now, but yeah, it's super sensible and other kind of AI models. I am aware it also supports some conversational models as well, and some other face recognition models or OCR models for license plate recognition, which is something we're really hard working on. And it also supports um, gesture recognition as well. And yeah, that's pretty much it. Yeah, anything really. There's no limit to it. Yeah.
This might be really quick.
Don't worry.
Your PCB has two power planes.
Yeah.
Why two? Are they different voltages? Are they what's the purpose?
All right. Here. Well, honestly, we have to because there are a lot of power plants, and we didn't have enough board area to make it in just one. We needed two. Yeah, that's the main reason. And to be honest, I made the hardware design that was like 1 year and a half ago. It was a long time ago, so I don't remember all the exact details. But I'm trying my best to answer them. Yeah. Yeah. Uh, sorry, I didn't hear you very well. Please, can you repeat it? Thank you. Well, it would have saved us a lot of time and effort to just use a computer model. But this was our first single board computer design, and we just really wanted to do it fully integrated. It was not a matter of whether it was worthy of or not. We just wanted to do it because, well, this is what we love to do anyway. So we wanted the challenge. That's the main reason. outside. All right. I'm just gonna finish very quickly. I think time went out faster than I imagined. I also want to thank Gabriel for developing. He took care of the application side of things, and the application you saw running up there, he worked on it, and he's currently improving it. And well, this is going to be pre-launched on crowd supply, and if it's not clear enough at this point, this is we are targeted this as open source product development kit, so people can buy and modify and make their own ideas with it. So that's the main purpose of this project. So right, that's all. Any other question? Thanks to you.